Since thermodynamics is dealing with phase changes, changing a material from a liquid to solid or gas, the phase of a material is directly dependent on the temperature of the material. It also depends upon the pressure to some extent as well. For example, we know water freezes at 0 degrees Celsius. It boils at 100 degrees Celsius. Both of these assume a pressure of 1 atm. The pressure actually affects these boiling and freezing temperatures. We're in Salt Lake City, Utah, or at least I am. That's a higher altitude. At a higher altitude, the pressure, the atmospheric pressure is lower. It turns out that boiling temperature is less than 100 degrees Celsius. It's not a whole lot less, but it is less. That means if I were to boil water to cook, say, noodles for spaghetti, I would have to cook a little bit longer than if I were at sea level, because the water's boiling at a lower temperature. It's not hugely different, so we don't see a big difference when it comes to cooking something like pasta. But if you've ever cooked baking, that seems to have a higher relationship, and sometimes you'll find high altitude adjustments on recipes or even on something you buy to cook and make. So technically, the boiling point, the melting point, does directly relate to temperature, which we'll talk about in just a minute as well. The inverse is true as well. If we can increase pressure, that increases the boiling temperature. It makes it higher than 100 degrees Celsius, which means the food is cooking hotter, which means it will cook faster. A pressure cooker, an Instapot, that's what they're taking advantage of, is higher pressure. They're increasing the boiling temperature and allows things to cook faster. So temperatures, we in the US at least, we typically, if you watch the news, you're looking at the weather, we are using the Fahrenheit scale. We are unique in that regard. Most places do not use the Fahrenheit scale. They use Celsius. Now, in terms of SI units, the Kelvin scale is what we end up using. And that's because absolute zero is 0 Kelvin. By absolute zero, we mean thermal energy is 0. So no motion of any sort could occur. So thermal energy of a system is always directly related to its temperature. The higher the temperature, the more thermal energy there is. And so this Kelvin scale, when we talk about thermal energy, technically on a microscopic level, we can think of it as the motion of atoms within like a gas or a liquid or a solid. This Kelvin scale shifts such that the coldest, absolute coldest anything can possibly be is 0 Kelvin. Now we can convert between Kelvin and Celsius we can find a temperature in Kelvin. So we're going to use a capital T to represent temperature, and then the subscript of K to represent Kelvin. To convert from Celsius to Kelvin, we simply need to add 273. Now, we do know this conversion more accurately, but our author, again, rounds it. We're going to use the 273 and not the 273.15. T sub C means the temperature in Celsius. T sub K means the temperature in Kelvin. To convert to Fahrenheit, the temperature in Fahrenheit and Celsius, the conversion looks like this. It's not quite as straightforward, but it's not hard to calculate. So T sub C means our Celsius temperature, T sub F means our Fahrenheit temperature. And so we can convert back and forth between those. When we solve problems, and we're going to find different, talk about different equations that have temperature in them, the safest bet is to put everything into Kelvin. If an equation has just T, it absolutely must be in Kelvin. But we will see a number of equations that have delta T, meaning a final temperature minus an initial temperature. It turns out the difference is the same whether we have Kelvin or Celsius, and it's because of this conversion. So for example, just making up a couple of numbers, let's say we had a problem we're solving. We're told the final temperature is 40 degrees Celsius. The initial temperature is 20 degrees Celsius. Delta T would be the final value minus the initial value, which would be a difference of 20 degrees Celsius. If we had converted to Kelvin first, so the 40 plus 273, and yes, I'm using my calculator because I don't trust myself at the moment, but I do know this is an easy addition. So this final temperature would correlate to 313 Kelvin. The 20 degrees would be 293 Kelvin. When we subtract and take the final value minus the initial value, we get a difference of 20 Kelvin. So delta T, as long as we're subtracting the Celsius temperature from the Celsius temperature, or Kelvin temperature from the Kelvin temperature, that change is the same. And again, it's because the conversion between the two is simply an addition. It's not a multiplication. So you can technically leave your temperatures in Celsius if your equation has a delta T in it. If you're worried you're not going to remember when you can and cannot, your safest bet is to always put every single temperature into Kelvin, because that will always work. Any problem, though, that has just T for temperature, it must be in Kelvin. You cannot convert after the fact because the conversion is an addition. All right, let's talk about phase diagrams for just a minute. So I've pulled from the book this figure. This figure is called a phase diagram. As I mentioned before, the phase of a material is whether it's a liquid, a solid, or gas. And for water, for example, we usually say 0 degrees is where it freezes, 100 degrees is where it boils, but technically that varies with pressure. So this graph on the left represents water. The 0 degrees Celsius, temperature is on the horizontal axis, and the 1 atm, pressure, is on the vertical axis. Where those two meet is in this dot. So these different phases, this left-hand side means the water is in its solid phase, meaning it is ice. This top right means it's liquid. Down here on the bottom right means it's gas. So at 0 degrees Celsius, 1 atm, this point is on the line that bounds the solid and liquid phase, meaning it is this temperature and pressure that allows for that change in phase. If the pressure is lower, for example, and we come over, we have to go to a different temperature to actually melt or freeze, meaning the water would melt or freeze at a higher temperature than 0 degrees Celsius. So this line right here is showing how the pressure and temperature are related in terms of being able to go between freezing and melting. So the melting temperature, essentially. Melting temperature depends on pressure as well. Now this diagram in the book, they say this is not drawn to scale. Just FYI. This line over here represents the temperature that would be boiling temperature. And again, that boiling temperature depends also on pressure. So these phase diagrams show us how pressure and temperature are related. These are known quite accurately. If you end up taking thermodynamics, you'll go more deeply into analyzing phase diagrams. For our intents and purposes, we want to recognize that pressure affects temperature at which a material will melt or freeze. Now, an interesting point on here is called the triple point. The triple point is where you can have all three phases, liquid, gas, and solid, at the same time. Now, for water, that's at a temperature of 0.01 Celsius and a pressure, so temperature of 0.01 Celsius, a pressure of 0.006 atm. That's a very, very small pressure, which is why this is something we would not observe normally. Now, carbon dioxide, on the other hand, this triple point is something that we can reach. If you've ever heard of dry ice bombs, this is what's happening. If you get some dry ice and put it in a container and it starts to sublimate, meaning going from solid to gas, the pressure will start to increase. And we can reach pressures and temperatures where we meet that triple point. And ultimately, the pressure just builds up more and more and more and more, where depending upon the material or the container the dry ice is in, it can just rupture the container. And that's why they call it a dry ice bomb. But ultimately, we've done this in a laboratory setting. Just have a teeny tiny piece of dry ice in a little plastic container, and you can see the vapors coming off and some liquid. And you can see all three phases in the container. So kind of interesting to be able to see that. This critical point at eventually a pressure and temperature that are high enough, the critical point is where if we get any higher pressure or temperature, we cannot distinguish between liquid or gas. The material can just easily go back and forth between liquid and gas, and it's not distinguishable just by looking at it. So these phase diagrams, these are known for a wide variety of materials, and we can look at directly how pressure and temperature are related in being able to change the phases. Now, another thing about water, it is unique in that the density of water decreases as it cools. This is unusual. This only happens around the 4 degrees Celsius and lower to the 0 degrees Celsius where it will start to freeze. This is why ice density is less than water, liquid water. And hence ice cubes float. Or a lake. Any ice that forms will be on the surface and not deeper down, unless the whole thing freezes. But the surface always freezes first. So water is unique. It's the only material that we know of that actually increases in density as it gets closer and closer to its freezing point. Most materials expand as they warm up and contract as they cool. And so that concept is called thermal expansion. So materials tend to expand, tend to get longer, like a rod. If you had some sort of metal rod, as it got warmer, it would also get a little bit longer. If you might have noticed driving over a bridge, for example, they have gaps between pieces of the concrete or asphalt. They're called expansion joints because we have a wide range of temperatures that we experience here. And so they try to build in this region where the roadway can expand without buckling. Now, we do see buckling sometimes in the summer where the temperature is so high that the sections, as they expand, they expand too much and they end up buckling up on each other. Of course, we don't want that. So they try to build in these expansion joints to allow for room for expansion. So you're going to see two equations for thermal expansion. For linear expansion, meaning the object is just getting longer, we use the change in length. So delta L represents how much longer, how much the length has changed. It can be shorter if it cools off. So our ratio of change in length over original length is going to equal a constant. This constant is called the coefficient of linear expansion. So it's this coefficient times the change in temperature. When you look at the test notes or within the book, you'll see some values for alpha for different materials. For volume expansion, our equation looks like this. The change in volume overall over the original volume is a constant. This is beta. It is a Greek letter. It is the coefficient of volume expansion. and then times the delta T. Thermostats used to be made of what's called a bimetallic strip, meaning this little thin piece of metal was actually two different materials together. They had different alpha values, different coefficients of linear expansion, so as the temperature would change, having different coefficients means they would change the length by different amounts, which means the end would bend in different ways based on which one had the larger or smaller coefficient. That change in temperature, in turn, allows for the thermostat to click on or off depending upon how you had it set. Now, these equations are an example where we have delta T, meaning we can leave our temperatures in Kelvin or Celsius as long as both of them are in Kelvin or Celsius. So let's do an example. So I have a problem here. A concrete bridge is built of 3 25-centimeter long concrete slabs with an expansion joint between them. The slabs just touch on a 115-degree Fahrenheit day, the hottest day for which the bridge is designed. What is the gap between the slabs when the temperature is 0 degrees Fahrenheit? Now, we cannot leave our temperatures in Fahrenheit. We do have to convert them. So one of our temperatures is 115 degrees Fahrenheit. The other is 0 degrees. I'll just actually call these 1 and 2. Our conversion, we have the temperature in Fahrenheit is equal to 9/5 times the temperature in Celsius plus 32. All right, so I have Fahrenheit. So let's bring the 32 over and then multiply by 5/9 so that this leaves us with just Celsius, so that we can convert these into Celsius. The 0 will be easiest. If we put in 0 for temperature Fahrenheit, we'll have negative 32 times 5/9. So we'll have negative 17.78 degrees Celsius. The 115, let's put that in. So this is 46.11 degrees Celsius. Since we're looking at just how the length changes, I just want to use the linear expansion equation. So we're looking for delta L. We need alpha. So I'm going to jump over. Let's jump down to chapter 18. Oops, too far. Little teeny tiny font down here. We have some coefficient values. Concrete here is listed as 1.2 times 10 to the negative 5th. The units are degrees Celsius to the negative 1. So alpha, 1.2 times 10 to the negative 5th. The Celsius to the negative 1 essentially is saying our units are 1 over degrees Celsius. So our change in length is going to be alpha L delta T. We have alpha. L is the length of that slab. Delta T is just our difference in temperature. It doesn't matter which one we put first because we're not necessarily talking about initial and final. Though, if we want to say our final temperature is this colder temperature and initial is the hottest temperature, we would take the final value minus the initial value. These are both in degrees Celsius, meaning they will cancel with these units in alpha. My answer is negative 0.019 So unit-wise, the Celsius are canceling. So the units right now that I left L in are the units on my answer. Had I put the 325 into meters, then I would come up with 0.00019 meters. We could say 0.19 millimeters. So this is not a big change by any means, but it is a change nonetheless. Now the negative sign here. The negative sign is because we are ending up at a colder temperature than what we started at. The negative sign means this slab shortened. It got shorter by this much. So it is shorter, it is smaller, so the gap is bigger. Ultimately, since the question is asking what is the gap between the slabs when the temperature is 0 degrees Fahrenheit, that gap would be 0.19 millimeters. All right. I want to go ahead and just double check my math because I make mistakes and I'm thinking I probably did here. So I'm going to run this through again. So negative 17.78 minus the 46.11, 25. Okay, I am getting something different this time. Let me run it through one more time. Unfortunately, I like to prove that I am human and make mistakes all the time. Okay, I'm getting this number again. So the gap is 0.25 centimeters wide at the cooler temperature, or 2.5 millimeters. We could put it in that terms if we wanted. The negative sign still means at the cooler temperature it is shorter. That gap, well, the slab is shorter, so the gap is now the 2.5 millimeters. Thermal expansion, a number of different applications. Thermometers, if you've ever taken a lab where you use a thermometer, just the glass one, they have, I think it's ethyl alcohol that's in here, dyed red. And then as the material gets hotter, this expands up the tube. And the markings on the edge help us to know what temperature the material is at.